Hello everyone, welcome to my YouTube channel. My name is Udevi Singh. I am studying in Sri Venkateshwara College of Engineering, Bengaluru, and I'm here to talk about the topic that is vector calculus. So let's start the video. Introduction to vector calculus. Vector calculus is a powerful mathematical tool used to analyze and understand the behavior of vector fields. It provides a framework for studying quantities that have both magnitude and direction, such as force, velocity, and electromagnetic fields. Vectors and vectors fields, vector quantities. Vectors are mathematical objects that have both magnitude and direction. They are used to describe physical quantities like force, velocity, and acceleration. Vector fields. A vector field is a function that assigns a vector to vector to every point in space. Examples include the gravitational field and the electric field. Visualizing vectors. Vectors can be represented graphically using arrows, where the length of the arrows indicates the magnitude and the directions of the arrow. Vector operations. Vectors can be added, subtracted, and multiplied in various ways, allowing for the analysis of complex physical systems. Scalar fields and gradient. A scalar field assigns a scalar value to every point in space. The gradient of a scalar field is a vector field that points in the direction of the greatest rate of increase of the scalar field. Understanding the gradient helps analyze how a scalar field changes in a space. The gradient gives the direction and magnitude of the steepest extent of a scalar field. It has important applications in physics, engineering, and mathematics, such as in the study of electric and gravitational fields. Divergence and curl. Divergence and curl are the two fundamental vectors field concepts. Divergence measures how much a vector field is spreading out from a point, while curl measures the rotation of the field around that point. Understanding divergence and curl is crucial for analyzing fluids flows, electromagnetic fields, and other vector-based phenomena in physics and mathematics. Line integrals. Defining line integrals. A line integral calculates the integral of a vector field along a curve or a path. It measures the cumulative effect of the vector field along the path. Parametric representation. To evaluate a line integral, the curve is often represented parametrically, allowing the integral to be computed using calculus techniques. Third, applications in physics. Line integrals many have applications in physics, such as calculating done by field, electric potentials, and fluid flow. Surface integrals. Surface integrals are used to calculate the flux of a vector field through a surface. This is important in physics for understanding properties like electric flux, magnetic flux, and fluid flow. The integral is defined over a parameterized surface in 3D space, allowing the calculation of the net flow of a vector field across that surface. Green's theorem. Introduction. Green's theorem is a fundamental result in vector calculus that relates a line integral around a closed curve to a double integral over an enclosed region. Geometric interpretation. Geometrically, Green's theorem states that the work done is in a moving a particle around a closed curve is equal to the flux of a certain vector fields around the surface enclosed by a curve. Applications. Green's theorem has numerous applications in physics, engineering, and mathematics, including the calculation of work, flux, and circulation in vector fields. Proof and assumptions. The proof of Green's theorem relies on the fundamental theorems of calculus and the properties of double integrals. It requires a certain assumptions such as the continuity of the vector field and the smoothness of the curve. Stokes' theorem, curl, measures the rotation of a vector field. Line integral integrates a vector field along a curve. Surface integral integrates a vector field over a surface. Stokes' theorem establishes a deep connection between the curls of a vector and the line integral of that vector. It states that the line integral of a vector around that field is equal to the surface integral of that field over any surface bounded by the curve. Gauss theorem, closed surface integral. Gauss theorem relates the flux of a vector field through a closed surface to the total or sink within the that surface. Divergence of vector field. Divergence of vector field represents the density of that outward flux of a vector field from the infinitesimal volume around a given point. Fundamental connections. Gauss theorem established a fundamental connection between the differential and integral property of vector fields, enabling powerful applications in electromagnetism and other fields. Applications and conclusion. Real world application. Vector calculus underpins a wide range of practical application from fluid dynamics and electromagnetic theory to computer graphics and image processing. Interdisciplinary connections. The principles of vector calculus find use in the divergence field, including physics, engineering, economics, and even biology, demonstrating its various relevance. Powerful analytics tool. Vectors calculus provide a mathematical framework for analyzing and understanding the behavior of the complex systems, making it an invaluable tool for problem solving and scientific inquiry. Continued advancement. As technology and scientific understanding evolves, the applications of vector calculus continues to expand, leading to the new discoveries and innovations across multiple disciplines. So this was my whole video. So thank you for watching the video. I hope you like the video. So thank you for watching the video.